All right, now, last time we did the Friis equation, right? Y'all did that, right? What my plans are today, I'm gonna take it to now the complete circuit. Here's the deal. If you have an antenna and it's transmitting, you got another antenna and you receive power. You learn how to get P received, but that is not the actual power that's available for loads. This is important. So please put this down. This is Friis part 2. All right. This is the bird thing. And then after this, we'll do a raise. So when we had an antenna, this is the transmitting antenna. And you could assume it transmits some P radiated. Sometimes it'll be in Dr. Wentworth's book, P transmitted at times. It's the total amount of power it's transmitted. If you're out a distance R away at some angle theta, then the actual power density here is equal to simply P transmitted or P radiated over 4 pi R squared. I always do it this way because if you get this down, a lot of stuff, it gets really easy. So that's isotropic, right? Then we have to multiply it by the gain of the transmitting antenna. So this antenna has a gain equal to GT, and remember, gain is really efficiency times directivity. So we're assuming, unless otherwise stated, the efficiency is about 100% or 1. Everybody follow me on that? If it's not, then you got a big problem. So this, and this will be a function of angle, that's the power density. Well, it'll actually, be a function of angular position. Could be a function of phi as well. This is the power density in watts per meter squared. And technically it's in the AR direction if you assume that this antenna is at the origin. I'm trying to keep this simple. Actually, let me get rid of that theta because it looks like it might confuse some people. This is just the gain in the direction that's associated with this point. Now, we put a second antenna down here. This is the homework. And this is going to be the receiving antenna. And this has some gain of the receiver. And now you want to find how much power is received. So we want the power received. And that's just PREC in Dr. Wentworth's book. And the way you always get this, and I tried to do this last time to show you the reasoning, I've got a power density in watts per meter squared. If we wanted power received in watts, we have to multiply it with something in the units of area. Y'all follow me? And that's the aperture. So I'm just going to call it AP here. And AP is the aperture. And the aperture is lambda squared over 4 pi times the gain of whatever antenna. In this case, the receiving antenna. Y'all follow me? Take note, it's proportional wavelength squared and proportional to gain. So just to make sure, yes, sir.
Can you, I'm a little bit confused. What are you writing there? Use AP minus aperture or AF minus aperture?
No, it means this is equal to the aperture.
Oh, I'm sorry.
My bad.
Okay, thank you.
That's a symbol for it. Now, sometimes you'll see A sub E. Different books use different symbols, but the meter squared will tell you the trick. I mean, it will tell you what it is. The units of meter squared. So P received here, and I'll just call it right here, P received at this antenna is actually equal to the average power density that's going to be incident on it times the actual aperture. And now I'll break it down for you. P received is actually, now I take this equation, and this is the standard form of the Friis. Usually they have P received over P transmitted. I'll leave it as just P received here for a reason. it's gonna be transmitted power over 4 pi r squared, gain of transmitter, that's just the power density. Y'all with me? Then you take that and you multiply it by the area, which is lambda squared over 4 pi times gain of the receiver. And the way this is usually rendered or stated is equal to P transmitted times gain of the transmitter times gain of the receiver. And then they'll just put lambda over, and you'll see 4 pi r, and this whole thing will be squared. Now please just realize this is just a compact way of writing this right here. Y'all see it, class? Group the 4 pi's, group r, group lambda, and square it. Now, there's one thing, and this is what you see in Dr. Winter's book. I suggest you put this in. This is also times the polarization efficiency, EP or E, I think he has EF in the book. And EF is really going to be the cosine squared of the difference in the tilt angles between the transmitter and the receiver. We went through that last time. Do you all remember the tilt angle has to do with the angular tilt difference off the axis? Remember, if you have two antennas, if they tilt like this one, say the vertical is measured at 0 degrees, it would be 0 minus the cosine of this angle, and you square it. Do you all make sense on this one? I'm just going through it. Okay. Now, I gave you homework problems regarding this. Did you all see them? Or not? Did they post or not? You did? Did you?
They posted, I didn't look at them.
All right, if you didn't look at them, I just want to make sure, you please try to do them. They're not hard, but doing them reinforces all this stuff, and you won't have that, less likely to have a brain lapse. The problem. So that's just the efficiency right here. Now, I don't worry that much about efficiency. Sometimes in the real world you have to. But this power, and here's the thing I want you to know. That received power is not how much you can get if you put a load on that second antenna. At most, you can get 1/2 of that. Do y'all hear me? Now here's why. So we're going to look at the receiving antenna. All right. It looks like this. And then we're going to put some load on it. Call it ZL right here. That's what it looks like. If you just have an antenna, I'm using a straight wire antenna, and you have some power density, some P, Av incident on here, it'll cause a certain amount of power P received right there to be equal lambda squared over 4 pi times gain of the receiver. And that's going to be times the actual average power density. Now, here's the thing. This is, I'm trying to show you a schematic where I draw a little kind of a cartoon of an antenna with a load. Electrically speaking, as engineers, what we probably look at this is this way. We're going to say that antenna itself will have some equivalent open circuit voltage. This will be an AC voltage. This will be the, please watch this. If you think about it, the antenna's got a wave coming in. If there was no load, there has to be an open circuit voltage developed. Do y'all agree with that? No current would flow. It should make sense. Now, the antenna has some antenna impedance. So it's going to have some Jx of the antenna. That's going to be a reaction. It's going to be the reactive component. Like with a half-wave dipole, it's what, 73.2 ohms is the real part of the antenna impedance, but then the imaginary is J42.5. Y'all follow me? So it's got some imaginary component, and it has some real component, and that's the radiation resistance. And this, right here, is what the antenna looks like electrically in terms of a lumped element model. We like doing lumped elements in electrical engineering because it simplifies our understanding. Now when we put a load on here, now the circuit looks like this. And this would be the voltage at the load, there would be current at the load, right? And you could say the power at the load was equal to 1/2 the real part of, really it's V times I, V load I conjugate of the load. But you're gonna see all this breaks down to a fairly reasonable thing. Does that make sense? Yes, sir. No. Does that make sense to everybody? So we're trying to get an electrical model of that antenna, of the effects of the antenna. Now, here's where I go back to circuits. Y'all had circuits, right? How many had Dave Irwin for circuits? All right, if you had Dr. Irwin, he probably really emphasized this. I've taught a course on circuits with him once. I was very impressed at his methods. The important things he usually goes over and really hammers home. When you look at this, this is like what? It reminds you of a circuit. You don't need to write this down, where you have some V source, and then you have some Z source, and you have some Z load, right? And the question is, what are the relationship between Z load and Z source to maximize the amount of power transferred? Do y'all agree with this? Now, think about the extremes first. If Z load is 0 ohms, how much power, if Z load is infinite, if it's an open circuit, how much power will be developed across the load? None, no current, no power, right? What if it's a short circuit, how much power? None, because what? It's V times I. V is 0. That's the definition of a short circuit. Doesn't matter what I is. Y'all follow me? So somewhere between a short circuit and an open circuit, there's going to be the sweet spot where the value of ZL will maximize that. How many remember that from Irwin? Or wherever you saw it, right? Now, the truth is, the value of ZL that maximizes power, write this down, ZL that maximizes power is when ZL is equal to the conjugate of the actual antenna impedance. How many remember that? Let me show you why, and I want to do it over there. But I want to make sure this really sticks with you. You don't need to write this, this is a little, it's information that's useful, and I think it helps clarify things. So let's just do this for fun. If you have a voltage Vs, and I'm going to have a source resistance Rs, and then I'm going to have a source reactance JXS. That's going to be the source right there. I come out here, now I'm going to have some load RL, some load resistance, and I'm going to even do this way because I know what the answer is going to be. Make this minus JX load. I know it's going to be that. Some of you know why. Because the conjugation implies that has to run. Now, if you look at this, just listen. I'm going to assume X of L is X of S. We can prove that if it's anything but that, you will not get maximum power. But if it is, then what's the total impedance looking this way? Class, just take a look. Well, the total impedance would be what? It would be RS plus JXS plus RL. So you got RL plus RS, right? And then it's minus JXL, right? Now you can sort of see if I make this impedance exactly the same in magnitude and opposite in phase as that one, they cancel. Do y'all got me on that? That's the reason. So Zn would just be RS plus RL. Now if I have that, the current I that would be flowing here that would be Vs over Rs plus RL, right? Y'all agree with that? And what would the power be dissipating the load. This is real power. I could calculate the voltage, right? But do I need it? How much power, average power, is dissipated by a capacitor and inductor, class? How many know it's 0? A capacitor can't dissipate power. It can store energy and can bring energy back. That's called reactive power. An inductor can store energy and it can't dissipate it. Only resistors can dissipate power as far as passive lumped elements. Y'all follow me on this, class? Now this is important you see this. Because on an interview, at times, somebody's going to probe you to see if you understand that. I've heard stories. My wife worked at Intel, and she told me one of the things, and my brother tells me this is true with Dianetics and other places up in Hudson. They don't want somebody who's a paper engineer, great scoring grades. They go there and they really don't know what they're doing. I'm just leveling with you. They want people that understand stuff. Grades are important in a sense to get you through the door, but they do not in any way, shape, or form dictate the path you take. It's your understanding. This is important. So here, if I wanted the power, that resistor is the only thing in the load that dissipates power. Do we agree on that? And this is only load power. So power in the load, remember that's a resistor, and this is AC, so this is really, that Vs is like the peak voltage, would be 1/2 I magnitude squared times R load. You all see that, class? I just took the current squared times RL times 1/2. Now, if you take Dr. Gross's power courses or anything like this, they'll use RMSI, so you forget about the 1/2. And generally speaking, in the real world, I usually use RMS, but in this book, he doesn't. That's the reason I'm writing it this way. Y'all follow me? All right. And just for the record, IRMS is equal to 1 over the square root of 2 times I peak for any kind of a sinusoidally varying waveform or cosinusoidally varying. Y'all remember that too? It's important you do. All right. So if I go ahead and do that, I find this is 1/2 I squared, I got Vs over Rs plus RL squared times RL. Now that's the power in the load, right? Who can tell me how you would figure out what values of RL and RS are required to maximize that power? Say for holding RL constant, what value of RS? Do you remember how to do it? Whenever we look as engineers for, if we got a formula where there's a peak and a minimum, what do we always do? Take the derivative of the function with respect to the axis it's plotted against, right? And set it equal to 0. That will either be the peak of the mountain or the minimum, right? So we would do that. I'm not gonna, I try not to bore you with this, but you would actually take the derivative of the load power with respect to, if we're talking about R load here, set it equal to 0. That's 1/2, and then it would be RL times the derivative of this. You can get Vs squared out front, and then you have the derivative with respect to RL of 1 over Rs plus RL. I'm just writing down what the derivative is. I factored out the constants. Vs is a constant, RL. You all with me? What's that going to be? 1/2, you don't have to do this, RL Vs squared, right? And then if I have this is really Rs plus RL to the -1, right? So it'd be -1 over RL plus Rs squared, right? And then the derivative of this with respect to Rs is 1. Agreed? Y'all follow with, you at least understand picking a derivative, setting it equal to 0. Correct, class? All right, set it equal to 0. And when I do that, here's the thing to know. You see how this all goes away. Y'all with me on that? That's just divide out both sides, equal to 0. Now I have this equal to 0, right? Or I should say, 1 second. When I do that, you know what, I forgot the 2. It'll come out to be 1/2, and I can take VS squared, you don't need to write this down, times RL. And then when I take a derivative of that, I get 2 times, in fact, let me do this. VS over RL plus RS right there. And then the derivative of that is going to be the minus, or now it's going to be that over 1 over RS plus RL. And when this is set equal to 0, you're going to find it happens to be a maximum when RL is equal to RS. And I know that for a fact. Do you remember that, anybody? You can prove that. Sorry. Running out of room, and actually, probably. No. Anyway, minus. Yeah. It will be for that. Now, here's the point, and this is the important part. When we look at this, the actual P received that you calculate with this formula, mark this down, please, in your notes and in your book. That is the maximum possible power received. Just put that down. This is maximum possible power received. But it is not how much power. It's the maximum possible power received, so that means that ZL, the load impedance, is actually the antenna impedance conjugated. So whatever the antenna impedance is, the load impedance to get maximum power has to be the conjugate of it. Does that make sense to everybody? Yes, sir?
What does that equation say, like on the bottom, I can't remember.
This?
Yeah.
It's RL equals RS for maximum power.
No, I meant on the VP of VOC equation.
Lambda square over 4 pi times
Yeah.
gain received.
I can put that again. It's lambda, the wavelength squared, over 4 pi, times the gain of the transmitting, gain of the receiving antenna, right there, times the actual aperture. Times the power density, P Av in the incident wave. And that's the P received. I'm just trying to say it's the area of the antenna you're hitting times the incident power density. Now, here's where it's important. All right, so that P received here, that's the maximum possible, but it isn't how much you're going to get. And here's how much power you're actually going to get for any load. This is important. So when I go over there, and if we assume it's matched, and this maximum power transfer, then what you find is this. You take a look at this equation. Well, I'll draw it right here, but I'll talk about it. Now I have plus the minus, and I'm gonna call this what Wentworth does. I'm not gonna call it the source voltage. He calls this the open circuit voltage that would occur across the antenna outputs if there was no load. Then you have the antenna impedance, right? And I'm going to just put R antenna, or R rad, the radiation resistance of the antenna, because it's assuming the load is the conjugate. And then you're going to have another. Now the load becomes R rad, the radiation resistance of the antenna. And now I want to figure out what the total power is received here, right? So if you think about the actual power received by this antenna. This system is the whole antenna. It's got the load and it's got the antenna impedance. And if you look at that, the total power received is actually equal to the actual, it would be 1/2 V open circuit squared, right? Divided by the radiation resistance, which is 2 rad. What I'm trying to do is say that if this is an AC circuit, right? If we wanted the power through resistor in an AC circuit, it's 1/2 V squared over R. V is P. Y'all agree with that? I mean, how many do, right? All right. Now the resistance is actually 2R rad because it's a matched circuit. So I have 1/2 2R rad, and we're after this. We're after V open circuit. So you can see that V open circuit, and this is how you do these problems, is actually equal to 4, please write this down, R rad, that's the radiation resistance of the antenna, times the power received, and it's the square root of it. And again, this right here is a theoretical thing. I mean, you can actually measure it if you have no load on the antenna and you use a high impedance voltmeter, you will measure that value. Y'all hear me? You will. But the thing is, that voltage itself is best estimated using this. The P received times radiation resistance. That's the truth, okay? Now, if you have that, that's ideal cases. So here's the thing. I found the power density, or the power density incident on the receiving antenna. I multiplied it by the area, lambda squared over 4 pi times the gain of the receiving antenna. I find the total power received. That's this quantity right here. All right. Now I get the open circuit voltage. And now if I put on any possible load, remember this was ideal, then the circuit I have is this. Remember, now I have the open circuit voltage, right? Now here's my antenna impedance. It doesn't matter if it has an imaginary part, but its Z antenna is here. That's internal. And now you hook up the load. This is the actual load that's measured. This would be V load. And now you put up Z load. With me? All right. Now, if I wanted V load here, and this is going to be the peak value, what would it be? Just take a look. Well, I got 2 impedances in series. Do we agree with that? So, and we got a voltage here, V open circuit. So this would be what? Just V open circuit, right? And it would be times ZL, whatever that is, over ZL plus Z antenna. Y'all agree with that? Think about it. Isn't that just voltage division? I mean, I could make it real and say, well, if this is plus or minus 10 volts, and this is 20 ohms, and this is like, say the load is 30, and I want this voltage here, that's just going to be 10, right? This would be V load. 10 times 30 over 50, right? Or a 6 volt. Yes, sir?
So is the ZN, is that just the real part?
No, no, hear me now. This is a great question. This is where people mess this up. We assumed that the imaginary parts had no effect with the optimal power transfer. That was the assumption, okay? Now, you have to use the entire antenna impedance here. If you want to calculate the actual current that would be developed across any load value or the power. You follow me on that? Now, that would be the voltage, right? That's peak voltage, magnitude, and phase, right? How would we get the current? It's as obvious as it looks. We'd say I through the load would be V open circuit divided by ZL plus Z antenna. Do you agree with that? Right? With me? And if I wanted the power dissipated by the load, what would I do? There are a couple of ways to do it. You all realize you could take 1/2 times the real part of V times I conjugate. You all with me on that? That's not necessary. Here's how you always get that. You go for this value here. This is how you get power dissipated at the load. Now that's straightforward, isn't it, class? Remember, that's the peak current. And then you say P at the load, power dissipated by the load, will just be 1/2. You take the magnitude of that current, and you square it, and then you just multiply by the load resistance. You ignore the reactive component. Y'all follow me? Because only resistors dissipate average power. Clear, class, on this one? Now, I want to say something. I know break's coming up. All right, I know we're going to have this fall break business. I would like to do one problem before I move on from here for one reason. If I don't, I have a feeling there are questions you have that you don't know you have. I'm always suspicious that, especially when you're thinking about other things, you're going to miss something essential. So I'm going to give us a problem. We're going to work it before I get into array theory, because array theory is not really related to this in a direct way. It's more mathematics, serious mathematics. But it is important. I was planning on doing that first, and I'm glad I didn't. So, here's the problem. Work with me on this one, it'll help you and me. I'm gonna take a half-wave dipole here. And I'm gonna, this is gonna be a half-wave dipole. I think I gave you a problem like this. This is gonna be a half-wave dipole. And there's gonna be a source voltage here. Call it 20 at an angle of 0 degrees volts. So really, this is the magnitude of V at an angle theta sub V here. You think of it that way. This half-wave dipole is an exact half-wave dipole, so the actual Z antenna here is going to be 73.2 plus J 42.5. This is reminiscent of something you saw in your quiz. All right. Now I'm going to go at 90 degrees. I'm not even going to mess around with an angle that makes my life difficult. And I'm going to let R be equal to 1,000 meters or 1 kilometer. These are nice round numbers. Then I'm going to put an antenna here, the receiving antenna. And this is going to be right here. This is going to be a half-wave dipole also in length. And it's going to be oriented where this is 90 degrees, so it's receiving the maximum possible signal strength. It's in the plane of the board. In other words, these things are aligned for maximum power coupling, all right? And then I'm going to put a load on here. And this load is going to be 30 plus J 20 ohms. All right? And what I want you to do, or what we're going to do, is we're going to calculate first the load. Well, this is where we're going. These are the questions that I would ask on a test or a quiz. These are very typical. These antennas might not be the same. There might be an angular displacement that's not 90 degrees, but this is the type of thing. I'm asking for the load voltage, magnitude and angle. Got me on that one? I'm asking for the current in the load, and I'm asking for the load power dissipated. And this is going to be average power, always average power. So, here's a question. Where do we start this problem? Well, that's where the information is as far as the source voltage, so start at the beginning, right? What's the first thing you think I'm going to do over here? Say again? How about if I make it even a little bit more interesting, let me put a source resistance here and I'll make RS at 100 ohms. That way we'll get a little more complexity, but not too much. Y'all follow me? So there's a source resistance, this power supply. There's a voltage here, right? What am I gonna do? How do I do this? Always look for the current. All right, got me on that one? So I want the current right here. I'll call it I transmitter, IT, right? What is IT? This would be a peak current anyway. Well, how do I get it?
20 over RS plus RREV.
Yeah, it's gonna be 20 at 0 degrees, which you can basically ignore, over 173.2, right? Plus J 42.5. Now, of this, the only thing you really care about is the magnitude. Can anybody give that to me, please? I'm really trying to do you a favor, showing you all the things that, do y'all agree with that? 73.2 plus 100 is 173. Okay? I just really need the magnitude, but I'll take the phase too for the heck of it. It shouldn't be a hard problem.
I can get it in my calculator.
Anyone? I appreciate you coming here. This stuff right here confuses people, I promise you. Say again?
So point your average.
111?
Point to
Oh,
eleven.
zero.
Point 11.
Sorry.
0.11 amps,
214.
0.11214,
Yeah.
and it's at some angle that I'm not gonna care about. You wanna give it to me or not?
-13.78.
All right. And that angle will not matter. Now, the next thing I wanna do, y'all agree that's the current, right? Now I wanna find the total power transmitted. Y'all hear me? Or radiated. So now I know P radiated from the source or P transmitted, either one, is equal to 1/2 magnitude of I of the transmitter squared times the radiation resistance, right? Y'all agree with that? Now that's a magnitude, and what I see people, I haven't seen it lately, people do, they'll take this number, if they get a real and imaginary part, and then multiply them together. You gotta take the magnitude, just the real part, just the magnitude you worry about. So this is 1/2 magnitude of 0.11214 squared. And what's the radiation resistance, class? 73.2, right? It's the antenna's radiation resistance. You don't put the source resistance in there. So the radiation resistance is 73.2 ohms, and this is gonna give us a power. Power radiated, what is it? Anyway.
.459.
1.459?
.459.
Okay. 0.459 watts, right? Okay, I got the power radiated here. What's my next step? What I really want is the power received here, don't I? Maximum power received. I can get that using Friese in one step, right? I could get the average power, and by the way, on tests I ask this, so we might as well do it. I usually ask for the average power density here. Now, how would you get that? Now, my next step is what? P average at the actual what? At the receiver would be equal to P transmitted over 4 pi R squared. Do you all agree with that? And again, that's the isotropic power density at the antenna that's receiving the power, correct? Then what do I do? There's one thing you gotta get right. If you don't know the numbers, don't worry. What do I multiply by? The
GFR.
gain of the
Receiver.
transmitter, right? Because we just want the power density here. Y'all with me? So the gain of the transmitter sharpens it. And the gain of the transmitter is 1.64. Now technically, you don't have to write this down. It's the cosine of pi over 2 cosine of theta over the sine of theta squared, isn't it? That would be the Yeah.
If you give us a problem like this on a test, do we assume 100% efficiency to get
Yeah, unless,
1.64?
I don't, now, here's the thing, if it wasn't 100% efficient, then this antenna, I'd have to give you something about the resistance of the antenna itself, not the source resistance. You follow me? Like in Dr. Wentworth's book, he puts copper wire with a certain radius at a certain frequency, so you can find the resistance of the actual antenna. I don't want to focus on that right now. All right? In always, if it's not stated, assume it's 100%. All right. So go here. Now this one right here is going to be 1, right? Y'all with me on that? So I just don't even worry about that. So I put P transmitted 0.459 watts over 4 pi, and that's 10 to the third squared, or 10 to the 6th, times 1.64. Now that's the power density received. What is that? Please. I'm not wearing this mask again. It's gagging. You can ask the question, don't worry. Just, did you have a question?
Where are you getting, oh wait, never mind.
Never.
I was
Yeah.
confused where the R is.
Where's 1.64 from?
Pardon?
Where's 1.64?
Remember the gain of a half-wave dipole is 1.64? Or the maximum gain, or maximum directivity, do you remember that? And for a half, or for a short dipole is 1.5 or 3/2?
I remember 1.5.
How many remember 1.64? Okay, it is, and you've had several problems on it. You have to kind of, I gave that to you on the quiz, but you should get familiar with that one, because it's used so often. All right, so what do you get for this? Because this is the power density on the second antenna. Anyone?
6 times 10 to the minus 8.
Anybody confirm that?
That's what I got too.
Okay, and that would be watts per meter squared. That's not real high. It's getting down to the point where just about into the noise floor, not quite. All right, now that's the power density, right? Now I need the power received. So what do I do to get power received at this antenna? Put it here. Power received at the antenna is what? The actual average power density incident on it times the area or aperture, right? And the aperture was what? Lambda squared over 4 pi times gain of the receiver. The maximum gain is 1.64. I'm just going to put 1.64 and I'm going to make it common. Now at this point, some of you are looking at this and you say, but we can't get the wavelength because we don't have the frequency, right? Just take a look. Y'all agree with that, class? So I'm going to give you a frequency, and you're going to like this frequency. 300 megahertz. Does anybody know why I chose that?
Lambda goes to 1.
That's right. Because now lambda is C over F is 1, and I like the number 1. I square it, I invert it, it's always the same. So now when I get the actual receive power here that I'm going to use, right? It's the average power density. That's 6 times 10 to the minus 8. That's watts. Times 1 over 4 pi, right? And again, the maximum gain or directivity of a half-wave dipole is 1.64. It's at 90 degrees. It is the max, right? So now I find out what this is. And you can give me that number if you don't mind. What is that?
7.83 times 10 to the negative 9.
10 to the minus 9?
Yes, sir.
Thank you. And that would be watts, correct? That's the received power.
Yup.
Y'all agree with this? Are you with me with how I'm going through it? It's methodical. Now that I have the receive power, now I can get the open circuit voltage for that circuit, the electrical equivalent circuit, right? So I'm going to draw that circuit up here. I know the receiving antenna will have a plus to minus V open circuit, and we're going to calculate in a second. And there's going to be Z of the antenna. Now this is an exact, I'm trying to make these two the same. So the actual antenna impedance of the receiving antenna is the same as the transmitting, or it's 73.2 plus J 42.5 ohms. So I'll go ahead and do that. And now here comes my load that I made 30 plus J 20. And I want this voltage. But first I gotta get the open circuit voltage. Anybody remember how to get the open circuit voltage? It's from this, right?
Square.
If it's the first time you've been introduced to this, you'll get used to it. The V open circuit used over there will be the square root of 4 times P received right there, times the actual radiation resistance. Now for us, it would be the square root of 4 times P received, or times 7.83 times 10 to the minus 9th, times 73.2 ohms. Square root of that, and I cannot do that one in my head for sure. Anybody want to tell me what that is?
.5 times 10 to the minus 3.
1.5 times 10 to the minus 3, and that would be volts. Remember, it's a peak value. Y'all with me? All right. Now, no. All right. What's this voltage going to be? I want you to just think about it logically. How many know? I've got 2 series elements and I'm looking for the voltage across one of them, right? I know the source voltage, right? What's this going to be?
Oh, it's the
It's
thing.
going to be what? V load is equal to 1.5 times 10 minus third of 15, or 1.5 millivolts, 1.5 times 10 to the minus third volts. Then it's times the load impedance, right? 30 plus J20 over the sum of these. So 30 plus 73 is 103.2 plus J. 20 and 42.5 is 62.5. And do you all agree that will be the load voltage? Do you all agree with that? Can you see it? All right.
Shit. Go.
We're not quite there. How do I get this?
VOC over.
Just voltage, right? VOC over the series, sum of the series impedances, right? So this IL would be equal to what? 1.5 times 10 to the minus third over
103.2.
103.2 plus J 62.5. Do you all agree with that? Did you have a question? If you do, please ask. Y'all follow me what I'm doing here? All right, the last thing. How do we get the power received at the load? By the way, that's the most important quantity in the real world. You always worry about the amount of power you're going to get to another component when you're transmitting. The voltage is something not really that important. So how do I get the power? Or by the way, if you can give me the magnitude of the current, I'd appreciate it. The load. Gosh, I'm over time. I just want to finish this, guys. Okay?
12.43 microamps.
12.43 microamps. Leave it as that. How much power is received at the load? Don't worry about the angle. Plus, anyway.
1/2 of magnitude.
It's going to be what? Say,
1/2 magnitude of
Right.
current squared times the real part.
1/2 magnitude of that, which is 12.43 times 10 to the minus 6, right? It's squared times the real part, which is just 30, right? And that would be the power. Can anybody complete that? Just give me the power. Do y'all follow me? I'm trying to do it sequentially so you see part. Did anybody do the homework problems? If you did, this is one of the homework problems I gave you, I believe. All right, what did you get for this? I mean, it's not the exact replica, but I mean the same principles all the way down the line. Did you get it? Anybody? I couldn't hear you.
Why are we using the VOC and IL instead of
VOC, what? Say again?
Shouldn't it be VL over the RL?
Well, you could do it that way, but if you take this over the sum of the two, wouldn't it be the same? If you take this voltage divided by the sum of the impedances, isn't it going to get the same current as V low divided by this? Okay,
Okay.
I just did it that way. You can do it the other way. Anyway, what do you get for this? I want to, yeah.
2.3 times 10 to the negative 9.
All right, I want to make a point. We got a little over 2 nanowatts. And how much did we transmit? Where was it? Erase it. How much power is transmitted?
0.45.
Half a watt. From 1/2 watt down to a couple of nanowatts at only 1,000 meters, right? That's nothing. Now, with high gain antennas, what you're gonna see is the amount of power I can get out at 1,000 meters. It may be only 1,000th of the actual transmit. In other words, it's a whole lot more. That's the purpose of high gain antennas. We'll do that next time, and I'll do a raise, but I wanted to get through this example. I think it's important.